Hello everyone, welcome back to the continuation lecture on nonlinear static analysis. So far in this lecture, I have been speaking to you on the difference between the linear analysis and the nonlinear analysis, and also I was taking you through the various different nonlinear analysis, and then we have also saw the material graphs, the stress strain graphs for various different materials, and we and I have also explained you the elastic and the plastic regions on the material graphs. So to continue further in this topic, I am going to speak to you the steps involved in the linear static analysis and the nonlinear static analysis. To start with, first of all, let's see the steps involved in the linear static analysis. As you can expect in any finite element analysis, the first and foremost step would be the setting up the model or building up the finite element model. First one is the cleanup of the geometry, and then obviously you have to build the finite element model, you have to mesh the model, and then using with the model, then you have to apply the material properties, loads and boundary conditions, and make the model ready for the analysis or the solver to solve the model. And then once you submit the job to the solver, what happens in linear static analysis is the solver, the very first beginning, it will check for the equilibrium of the structure, whether it is in static equilibrium. Since it's a static load case, it makes sure that the static equilibrium within the structure is established, and then based on that it applies the loading, and then it solves the problem and computes the displacement, strain, stresses and forces and free body loads or whatever the user might have requested. And finally the user could able to view the results or check the results with his rough calculations during the post processing stage. This is a typical steps involved in the linear static analysis. So now we'll move to the nonlinear static analysis, where the first step is exactly similar to what we have done before. It's just setting up the model. Again, you have to have the geometry cleaned up, and then meshing, applying the material properties, loads and boundary conditions, and then having the model ready for the analysis. Now there will be a little bit change in the second step, in the and the third step in the nonlinear analysis. In the second step, what typically happens here is, since it is a nonlinear solution, it will the loading will be the loading applied to the model will be in a consecutive steps in an increments. So what happens is solver will start to solve the problem once you submit the job to the solver, and then first the solver will check the equilibrium of the structure, make sure that it's a static problem, it's not a dynamic problem or a rigid body motion problem. Even though if it is a non-linear, but still it is a static problem. And then once the equilibrium is established, it is an initial equilibrium. Then what will happen is the nonlinear solution within the solver will start its own process. It will have some methods to follow. Some of the famous methods are Newton-Raphson method for nonlinear static problems and arc length method for the buckling problems. So it will apply the load in a very small increments, and then it will, for example, the total load on the structure is 100 newtons. Suppose you are mentioning to the solver, or you have specified, you have given the options while running the model, saying that you want your load to be applied in 10 increments. Then each time the solver will apply 10 newtons. First it will apply 10 newtons, and then it will solve the problem. it will extract the forces, and then finally the second iteration, it's like a loop. It will go back and it will apply another 10. So 10 and 10, existing 10 will become 20. Now it will solve and it will go back to the loop again where the load applies, and it will apply another 10, that will become 30. So similarly, till the maximum load or the maximum specified load is reached, the loops run. So in that way, it is an iterative process where it solves the problem and finally computes the displacement, strains, stresses and forces, and whatever any additional output the user has requested. Finally, what will happen is, like, once the nonlinear solution is converged or solved, it is the duty of the user to make sure that the results make sense, the results are valid, by using simplified assumptions and simplified rough calculations. You should be able to check and verify the results that it is correct. So that's the fundamental difference between the linear and nonlinear static analysis, where in nonlinear static analysis the load increment is done in steps. So now we'll move into the parameters that is required for running a nonlinear analysis. So for any nonlinear analysis, first we need the static load condition. So that should be mentioned in the case control section of the BDF file. We need the load command, and finally there is an NL param command, which is the nonlinear parameter command, that will select the iteration method. So the famous one for the nonlinear static problems is the Newton-Raphson method, which is widely used within the engineering community. And then in the bulk data section, there will be a corresponding NL param that specifies the time step or the incremental steps, in how many number of increments the load has to be applied. And NLPCI command is for the arc length methods, which is typically used for nonlinear buckling. And the param LJ displacement, LJ displacement stands for large displacement. This is used for large displacement problem or the geometric nonlinearity problem. So some of the important considerations would be, a solution number is 106, which is for the Nastron run. For the linear static, it is solution 101. For the linear buckling, it is solution 105, and for nonlinear static, it is 106. So 106 should be selected. So the parameter large displacement should be specified for any geometric nonlinearity, and any nonlinear material data, including hyperelastic materials, should be explicitly specified. And for those material nonlinear things, we have to specify the tangent modulus or secant modulus that should be defined, or the stress strain curve that gives the clear value of the variation of stresses and strains when the material goes into plastic region, that should be specified. And then if you have used any gap elements or rigid body elements, that should be watched out, how the connections between the members the during the nonlinear run, that will change. And any contact elements, I haven't covered much on the contact analysis, but the if you have used any contact elements within the model, that should be defined properly. And in terms of controlling the iterations with nonlinear param, the within the nonlinear command entry or the code, we have semi method, which provides the better convergence than the auto method. Auto method is the automatic increment of the loading, when the FE tool itself calculates how many increments is needed and when what kind of increment is needed, and semi method is a opposite version of the auto method. But semi method takes a higher computing cost, in the sense it occupies it takes a bigger buffer memory to run, and then in terms of time uh, time taken for the runs, both are similar. It depends on the bigger the model, it depends on the whether the model is big or small. Bigger the model, bigger the time taken to solve the problem. And then the tolerances for the convergence criteria should be somewhat conservative, in the sense that is the plus or minus variations to the results, what is expected and what is obtained. And moving to the iterative methods, we have Newton-Raphson and modified Newton-Raphson and secant methods for the load increments. I have mentioned that the Newton-Raphson is the best one and effective one, and which gives a most accurate solution and a quick solution for the most nonlinear static problems, and arc length method for the nonlinear buckling problem. So this is a typical command line or a card for the load, static load. This specifies this load command, load card entry will is used for the combination of static loads specified in the static load case. So what we have for the command is, we have the set identification number, and then it's the overall scale factor. You can change the scale factor over here in the BDF, and then these are all the scale factor for the local set identification number. This is a local set identification number. It combines multiple loads into one applied loading, and this is the NL param card, which is used for nonlinear static control, where we have the set identification number, and NINC is the number of increments that is required to apply the load, and then the incremental time, and K method stands for the semi method or iter method or auto method, and then K step is the number of iterations required, and the max iter is the maximum number of iterations required. Only we might be using only the few steps, and few other things are for the maximum stress levels and maximum tolerance, and in terms of strain, plastic strain, those parameters. So one of the important thing that we need to watch over here is the method we select for the nonlinear run, whether it is a semi method or auto method. That depends. Auto option is the most efficient one, and then next to the auto option one we have iter one. Iter is also, iterative method is also very efficient one. So we know that the nonlinear static run requires the solution sequence 106, and then if it is a large displacement problem, then you have to select the large displacement. So I'll just move into the patron demonstration, and then we'll solve a problem completely, and then I'll open the BDF file. Once we build up the finite element model, once we generate the BDF file, and then I will take you through the BDF file showing the nonlinear parameters and nonlinear time steps that we have specified within the patron in terms of load increments and the time step increments, and then we can discuss further on this topic.